When running a phylogenetic analysis, it's not unusual to find a taxon that's very difficult to place, perhaps because it's got a lot of missing data, or maybe the data conflicts with signal elsewhere in the tree. It might be the end of a long branch. There are all sorts of reasons we might end up with a taxon being hard to place on a tree, but these taxa can cause a problem when summarising the rest of the phylogenetic results. So these are rogue or wildcard taxa. And here's an example where we've got a set of trees. Maybe these are bootstrap trees, maybe these are from the base and posterior sample, and these trees agree on the relationships between taxa 1 to 4, but disagree on exactly where the rogue taxon X should be situated. And if we take the majority rule consensus of these equiprobable trees, we end up with a star topology that gives us no information at all about which tree our analysis said was more probable. However, if we omit taxon X before making our consensus summary tree, we can come up with a reduced consensus tree that reveals that all of our input trees agree on the relationships between taxa 1, 3, 2 and 4. In this case, this clearly gives us more information than our plenary consensus that includes all the leaves. By including X, we lose the ability to resolve a lot of information. So we want to generate, if we're going to generate a single tree to summarise our distribution, we want to generate a tree that contains as much information as possible. Our plenary tree here doesn't really communicate anything. Any of the 15 5-leaf binary trees are consistent with this plenary tree. Whereas the reduced consensus tree rules out some trees. There are only 5 of these 5-leaf binary trees that are consistent with it. And therefore we've got more confidence about which tree is the true tree according to the phylogenetic results we're trying to summarise. And this increased confidence means that we've gained information about the true tree. So that was a simple case. It's not always easy to determine, though, which of a pair of consensus trees is the more informative. So taking again here our reduced consensus tree, this is the same topology we just saw, we've got certainty that taxa 1 and 3 are separated from leaves 2 and 4. So that gives us some information, but it doesn't tell us anything about where X might fall. Whereas the plenary tree surely tells us a bit more. We know that 1 and 3 are separate from X2 and 4 with a 60% probability. And our 60% support value also applies to the separation of 2 and 4 from the other 3 leaves. Now, it's a little bit tricky, however, to really interpret what this tree might be telling us about the relationships just between 1, 3, 2 and 4. Do we multiply together these support values? 36% sounds a little bit low. Do we take the highest of the supports? What's it telling us about the relationships between the taxa excluding X? It's also not entirely obvious what it's telling us about the position of X itself. If I just look at this tree, my first thought is, well, X is situated within the middle of this tree with a probability of 60%. Well, that's not quite true. These trees are examples produced by Mark Wilkinson and by Crotty to demonstrate the complexities, actually, of interpreting these trees. They've been generated by adding the rogue taxon X to all 5 of the possible positions it could occupy on the 4-leaf tree, uniting 1 and 3 to the exclusion of 2 and 4. In other words, we have no information at all on the position of X. And as such, we're forced to admit that the reduced consensus, which reveals the unanimous support between the relationships of 1, 2, 3 and 4, is more informative than the plenary consensus tree. What general principle can we apply to quantify how much information there is in an arbitrary consensus tree that we're presented? Well, if we're interested in the amount of information, it makes sense to use Shannon's formal information theory. And so I'm going to use Shannon entropy here, which is a measure of the average amount of information within a set. And the set I'm going to be interested in for the example is the set of all 15 possible binary trees on 5 leaves. We've already met 5 of these. And the amount of entropy is calculated using Shannon's famous formula. And we can stick in the numbers. There are 15 trees, they're equiprobable, so we get 3.9 bits of entropy or uncertainty. What this means is, if we want to narrow down the set of trees to have certainty that one tree is the true tree, we need to gain 3.91 bits of information. A reduction in the entropy of a tree set corresponds to an increase in our information, in our ability to guess which the true tree really is. So let's work through this familiar reduced consensus tree to work out how much information it would contain. Well, it narrows down our set of trees from 15 to 5, which is still equiprobable. And so we can plug 5 in place of 15 in our equation, and that reduces the uncertainty. There are 2.3 bits of uncertainty remaining. That's reduced our uncertainty by 1.59 bits. We've gained some information from this consensus tree, and we've formally quantified it. Now let's look at the plenary tree, which is a little bit more complicated. We've got a couple of splits here. Let's just look first of all at the split dividing 1 and 3 from the other 3 leaves. Well, there are only 3 5-leaf trees that contain this split. So if we knew for sure that this split was in the true tree, we'd have reduced our uncertainty considerably. We'd have gained 2.3 bits. But we don't know it for sure. We only know it with a 60% probability. So we need to incorporate this reduced probability into our entropy calculation. We've got to go in each of the p's, needs to be reduced by 60%. And this reduces our information content. But what about the 40% chance that our tree is not one of the 3 trees that contains this split, but in fact one of the 12 trees that doesn't? Well, again, we've got a 40% chance of this happening that we need to build into our formula. We need to work out how much uncertainty there is associated if we did know it was one of these 12 trees, and modify that again with the 40%. Once we've done that, we've got an equation we can put into the computer, and this tells us the uncertainty associated if we know this split has a 60% probability of occurring in the true tree is actually quite high, 3.3 bits. So we've not gained much information, just half a bit from this split. But don't worry, there's more than one split in this tree. We've got a symmetrically identical split dividing 2 and 4 from the other taxa, and that will yield, of course, the same amount of information, another half a bit or so. So if you want to know the total information in this tree, well, we can just add these up together, can't we? And that gives us 1.1 bits of information. Now, my maths teacher used to give me a sarcastic gold star when I did something mathematically questionable, and this is gold star mathematics. You can't just add up the information content of each split, because the splits aren't independent. So let's phrase this as an approximation of how much information there is in a consensus tree. And actually, I think this is a reasonably okay thing to do. The amount of information by this approximate measure, it does increase more or less monotonically with the actual amount of information calculated properly, but it's much, much easier to calculate things this way. It's kind of impractical to get an exact value as trees start to get large. So this is a reasonable approximation. It's good enough for our purposes, I argue. So we've got a way then to work out how much information there is within any given consensus tree. And we've used this to compare trees and to decide, okay, well, we do really prefer this reduced consensus tree in this situation, as Wilkinson and Crotty argued that we ought to. But this is a very simple example. It doesn't take long to consider all the possible trees. Things get a little bit more complicated when we've got larger trees, and our goal is to consider all possible consensus trees we could draw and to report the one that has the most information about the underlying tree set we're trying to summarise. To consider all possible trees, well, the number of trees we need to consider increases roughly with n factorial. We've got to consider the plenary that contains all the leaves. We've got to consider, well, there are n trees with 1 leaf missing. Or we could take 2 leaves out. Well, there are roughly n squared pairs of leaves. We could take 3 leaves out. this is a large number of possibilities to individually evaluate. So this becomes impractical pretty quickly. As a result, we're led to rely on heuristic approaches, and one that's been used to great effect by Abera and colleagues on an equivalent problem starts off by saying, well, let's just take each leaf in turn and we'll just drop the leaf that gives us the most information. And if dropping a leaf doesn't gain the information we've got, we won't do that, we'll stop. And we repeat this until dropping a leaf, we can't gain any further information by dropping another leaf. This is a pretty good approach, actually, but it hits into a snag, which is that it's defeated when we've got a pair of rogues. So looking at the tree set here, if I just remove X, well, Y is still going to have an uncertain position and reduced resolution. If I just remove Y, I'll be left with X. I need to remove X and Y in order to reveal the unanimous agreement in the relationships between leaves 1 to 6. So maybe we could try, once we've dropped one leaf at a time, we could try dropping 2 leaves at a time. And of course there are something like n squared pairs of leaves, and so the complexity increases quite a bit. And well, maybe actually there's a Z as well, and we have to remove 3 leaves at a time, so we'd have to increase that drop set, that set of taxa that we're omitting at each stage. So this becomes less and less heuristic and more exhaustive. It's not going to guarantee us an optimal consensus tree, but it is actually a very effective method that can be implemented pretty effectively. There's another heuristic we could use, which I've tinkered with, and one thing what we could do, the way this works, is we look at the stability of each leaf, which we can measure using some measure of how variable the graph geodesic is. I won't go into the details. We rank leaves by stability, and we drop whichever leaf is the least stable across all of the input trees. And then we calculate leaf stability on that reduced set of trees, and we keep on going, dropping the least stable leaf in turn. And we're going to get a list of leaves in the order we dropped them. We keep on going until we can't improve the score any further. So we're going to drop X here, and then we're going to drop Y. And dropping X actually lost us information, but then we gained that back when we dropped Y. So we keep on going down the list, and then we work our way back up the list again, because maybe we're a little bit too ambitious and remove too many leaves. Maybe there are some leaves that individually we can restore and gain information as we work our way back up this list. So this is more or less scales in line with the number of leaves, so it's much quicker. In many circumstances, it's less likely perhaps to find an optimal drop set, an optimal set of rogues to remove. Does this work in practice? Well, I took 140 data sets where Abera et al. Used these data sets to test their Rogue-Narok method. They simulated 200 bootstrap trees from simulated genetic data sets with a known true tree, and asked the question, does deleting rogues improve the quality of a consensus? I've measured the precision and the accuracy here with Rogue-Narok, the best existing rogue detection method, my fast heuristic using my information-theoretic definition, and a slower heuristic modelled on the Rogue-Narok approach. And what we find is that, yes, my information-theoretic criterion for evaluating the quality of a potential consensus tree yields consensus trees that are better resolved and that are more similar to the true tree, that is more accurate in the relationships they reveal. And the quick heuristic approach is actually pretty good, despite having a much faster runtime than either of the other approaches. This is all implemented in the R package Rogue, which is available for download from the CRAN repository. And if you're interested in using this, if you find it useful, I'd love to hear from you and discuss it further. Thanks for listening.